This is a demonstration of interactive petrophysics. In the next 10 minutes or so, I will be showing you how easy and quick it is to interpret wells using this software. The dataset being used is a demo well provided with the software. 1100 feet of data will be interpreted at 2 samples per foot. Data can be loaded into interactive petrophysics in ASCII, LAS, LIS, and DLIS formats. In addition, direct links are provided into other third-party databases like OpenWorks and GeoFrame. This analysis dataset will be loaded from a LAS file. The user selects the file to load and then chooses the curves. In this case, I'll select all curves. Quick plots of the data can be made by selecting one of the predefined formats. Here I'll select the triple combo. The well consists of sand shale sequences with 2 hydrocarbon zones, easily seen by their high resistivities. The user can zoom to any part of the log by changing the scale in the scale box. The right-hand track gives an overview of the loaded well data. By clicking in the track, one can easily move to any part of the well. The bottom part of the window gives the current values of the data at the current cursor position. The analysis is made in 2 parts. Firstly, a calculation of clay volume using multiple clay indicators, and then a calculation of porosity and water saturation. To perform the clay volume analysis, the user selects the clay volume module. Here, the user selects the type of clay indicators to be used. I'll select gamma ray, resistivity, and neutron density. The clay volume interpretation plot is displayed. One track is made for each indicator, plus the result track, 1 curve per indicator. The vertical lines seen in the tracks, like the gamma ray track, represent the clean and shale parameter picks. By placing the cursor on one of these lines, one can pick it up and drag it to a new position. When the line is let go, the program instantaneously recalculates the zone and shows the results in the result track. By right mouse clicking in a track, a pop-up menu can be displayed where histograms and crossplots can be selected. I will select the gamma ray histogram. The vertical lines in the histogram are the clean and shale parameters. The user can select the line and change the parameters. The zone is recalculated and the results are displayed. For the resistivities, I will set the resistivity clay and clean lines. The neutron density indicator is best done through crossplots. The clean line and the clay line are displayed. The user can pick up either end of the line to change the values. The parameter values are displayed at the base of the crossplot. In this well, one can see a light hydrocarbon effect. The clean line therefore needs to be zoned so that the slope can be changed in the hydrocarbon zones. The zoning is done by clicking in the zone track to the right of the depth track. I will now zone the well to separate out the hydrocarbon zones from the water zones. Returning to the neutron density crossplot, one can see the new zones are displayed on the right of the crossplot. By clicking in the zone boxes, one can change the view. The parameter lines now represent the active zone. The active zone is displayed at the top of the crossplot. One can change the active zone by clicking the Active Zone button and then selecting a new active zone. More than one active zone can be selected at once. Here I'll select Zone 2 and Zone 4, which are the light hydrocarbon zones. I will now change the clean line to take into account the light hydrocarbons. One can turn on and off individual clay indicators by zone, by clicking in the track and selecting the Turn On Off function. Individual parameters can be selected and changed by zone. When the user is comfortable with the interpretation, the porosity and water saturation module is selected. The porosity and water saturation input window allows the user to select the input curves to be used, the default porosity model and the default saturation model. Here I'll select Indonesian and the default temperature units. Click Run to start the calculations. The program asks whether I want to copy the clay parameters from the clay module. I'll say yes. The porosity water saturation interactive log plot is shown. The second track shows the zones from the clay module. The next track is the neutron density and sonic input curves with their clay parameters. Next is the resistivity curves and their clay parameters. RW apparent and RMF apparent. Matrix density, water saturation curves, porosity curves with a movable oil plot, and finally a lithology plot showing sand, shale, and in green, silt. The program uses default parameters for RW, A, M, and N, which are not correct for this well. RW can be set in several ways. By changing the RW parameter line, this can be dragged to line up with the RW apparent curve in the water zones. Another way of setting RW is by using the RW apparent histogram. This will allow setting of RW in all zones at the same time. Change the active zones to all zones and move the RW line to line up with the wet sand peak. One can see that all the residual oil has now gone from the wet zones. RMF can be set in the same way using the RMF apparent histogram. Resistivity clay can best be set by using the resistivity clay volume cross plot. I will set the same resistivity clay for all zones except zone 1, which has a different clay resistivity. RXO clay can be set in a similar way. Picket plots can be used to interactively set RW and M values. Here, the default value of M of 2 works well. Water saturations look good now, so let us zoom into the upper hydrocarbon zone to look at the hydrocarbon density. In the matrix density track, one can see that the calculated matrix density is around 260 grams per cc, where it should read 265 for sand. This is because the default hydrocarbon density is set at 0.8. By moving the hydrocarbon density parameter line, one can adjust the hydrocarbon density to give an average matrix density of about 265. Zooming to the lower hydrocarbon zone, one can make the same sort of adjustments. Zooming out to the whole well, we can see that we have a reasonable interpretation. The cutoff and summation input window allows the user to select up to 10 input curves to provide discriminators for net pay and net reservoir. I will leave the defaults for porosity, water saturation, and clay volume. The three main tracks are the input discriminator curves, porosity, water saturation and clay volume. The green flags represent the net reservoir, the red flags the net pay. Porosity cutoff can be set by dragging the cutoff line in the porosity track, or by moving the vertical line in the porosity histogram. Clay volume and water saturation cutoff values can be also changed in similar manners. Crossplots can be used to set cutoff values. This is the porosity clay volume cutoff. Once the cutoffs are set, the well can easily be zoned by splitting the zones in the zone track. Zones which are not needed can be deleted. Zone tops can easily be moved to align them properly. Parameter listings of the results can be seen. Changing the cutoffs will instantaneously change the results in the listing. This has been a very quick demonstration of some of the many features of interactive petrophysics.